right? Pyramids, columns, okay?
Columns?
These, in between the pyramids. Okay, now you have the minor calyx. This is a major calyx over here. This is the renal pelvis, this one, right? Right here, right? And then you have the ureter. Okay, now. So in the column, and in between the columns of the pyramid, so you go over here to a pyramid, right? So now you have the tubules. You have the, again, you have the glomerulus inside, the capsule is on the outside, proximal convoluted tubule, descending limb, ascending limb, distal convoluted tubule, collecting duct, papillary duct. Okay? And these papillary ducts, they all come down and they end up down here in the renal papilla, which is beginning of the minor calyx. Okay?
And these are the afferent?
These are afferent arterial. These are the efferent, right? See, they go into the capillary bed. See, so the kidney really has two capillary beds in it, right? A fenestrated capillary bed because it's a portal system, and a standard capillary bed here. Because actually, physiologically, the peritubular capillary bed is doing a lot of the work. See, because what happens is that the glomerulus is filtering everything that's soluble, right? And it's a lot of good stuff. Glucose, ions, amino acids, everything, right? Plus the waste. So now, the first step is it goes into the proximal convoluted tubule. The proximal convoluted tubule is going to reabsorb all those nutrients at their homeostatic limits. Okay? So what happens is that, you know, how you remember proximal convoluted tubule is really, if you look at the right-hand column of a blood test, and you see those numbers like 70 to 120, you know, 12 to 26, you know, all this stuff, right? That's really set, that high number is really set by the proximal convoluted tubule. It's like how much nutrients can it reabsorb in the time it has, okay? Right? So, for example, like glucose, we think of it as 70 to 110 milligrams per deciliter. Well, it's because the transport maximum of the proximal convoluted tubule is about 110, 120 milligrams per minute. Okay? So anything above that 120 stays in the urine. Hence, diabetes mellitus. Okay? But they all work like that. Calcium, vitamin C, sodium, potassium, everything. All has a transport maximum in the proximal convoluted tubule. And therefore, anything above the homeostatic limit gets filtered. Okay? Because that's the most of them are the transport maximum. So now what happens is now you go down the descending limb, ascending limb. What the ascending and descending limb does, it does something called the countercurrent amplification effect, which you'll see in lecture. And basically what it does is, the end result of this is that it excuse me, that it conserves water. So this is an osmotic system where if the tissue is saturated, the medulla will be saturated. So therefore, not too much osmotic pull. There won't be too much osmotic pull to drag water out of the tissue, right? Out of the tubule into the tissue. If it's dry, if it's dehydrated in here, obviously you get a huge osmotic pull to pull all the extra water out of the tubule back into the tissue, where it gets picked up by the peritubular capillary bed, goes back to the body. Now, after that, the water conservation, then we have the you gave me a defective stick, dear. Bad stick. Okay, anyway, no, I flipped it over. I just had to make fun of her just because I can't. This is what makes my heart beat. Okay, so now, keep my heart beating. Anyway, so there's the distal convoluted tubule, right? Distal convoluted tubule. The thing there is, that's where you have hormonally driven reabsorption and secretion of materials. So this is where the hormones work. ADH, aldosterone, calcitriol, all those hormones you're learning about now. HGH, right. They all work at the distal convoluted tubule. Either it's going to move glucose or sodium or whatever. okay? Or calcium, okay, depending on what hormone you're looking at. So, and that's going to be in water. And then what happens, and then you get to the collecting duct, which is over here, right? And the collecting duct now is going to do the same thing as the distal convoluted tubule. Same exact thing. Hormonally driven reabsorption secretion. And then you have the papillary duct. Now once it reaches the papillary duct, we stop calling it filtrate, start calling it urine. Because once it's in the papillary duct, it's done. All the modifications are finished. Only the nephron can modify the filtrate. After you get out of the nephron, you're done. Whatever's in there, staying in there. Okay? So what do you have in the papillary duct in a normal, healthy kidney? You have the 3 nitrogenous wastes, right? Creatinine, urea, and uric acid. Okay? Then any excess glucose or excess nutrients or extra water. Okay? And it goes down to the papillary duct and into the papilla and into the myocalyx and out. Okay? Okay, good. So that is the thing. Now, here we have this. Now, this is an interesting thing, this model. What will happen, we have the afferent arteriole, the efferent arteriole, and glomerulus. The pressure goes in, pushes out into the capsule, gets collected in the capsule, starts to flow into the proximal tubule, into the nephron. It goes down, it comes back up. This is the distal convoluted tubule. See? So it goes down, comes back up. So now, right in here, in this triangle, right? They don't show it on this model. But right here and there in this triangle, and on the walls of the afferent arteriole and on the triangle, is a structure called the JGA, the juxtaglomerular apparatus. The juxtaglomerular apparatus is really important because it sees the pressure of the blood coming in, the pressure of the blood going out, and the product, the filtrate you created with this pressure. Juxta, J-U-X-T-A, juxtaglomerular, glomerulus, L-A-R, right? Glomerular apparatus, A-P-P-A-R-T-U-S.
Where is that?
It's right here.
What did it do? The pressure?
What? Okay, now. Well, you got to do it, okay? And it's looking at the pressure of the blood entering and leaving, which tells you about the rate of filtration. And then it's telling you about, and it looks at the distal convoluted tubule, the product, what you have in here. So if you have a lot of nutrients, you can adjust your hormone levels to get them back, right? If you have too much water, you can get the water back. If you don't have enough water, you can keep, depending on the body conditions, right? So now, there's a hormone that's released from the juxtaglomerular apparatus. It's called renin, R-E-N-I-N, renin. Renin stimulates the angiotensin pathway. Did you learn about the angiotensin pathway yet?
No.
Okay. Well, if you haven't, renin, what it does is it goes through the whole body and activates this big pathway that affects almost every organ, and it's called the renin-angiotensin pathway. Okay? One of the steps of the renin-angiotensin pathway is goes to the posterior pituitary and stimulates the release of ADH from the posterior pituitary, antidiuretic hormone, which goes to the distal convoluted tubule and tells it to absorb more water. Antidiuretic hormone, less diuresis. Okay? Then you have another step of the same pathway where the angiotensin 2 will go to the adrenal cortex and cause the release of aldosterone. Aldosterone goes to the distal convoluted tubule and tells it to reabsorb sodium. When you reabsorb a lot of sodium, where's the water follow? Out, right? Okay? So that also drives up blood volume and blood pressure. Okay? Because the bottom line is the glomerulus needs a certain amount of pressure to work, right? So if the pressure drops, it activates all these other mechanisms to drive the pressure back up. Okay?